Picture this: a single point of light in the infinite black, flickering against the void. Then, in an instant, it explodes outward with unimaginable force, birthing galaxies, stars, and the very fabric of space and time itself. What could unleash such raw, universe-shaping power? The answer lies in the invisible forces that rule the cosmos, silent, relentless, and far more extraordinary than anything we experience here on Earth. From the crushing grip of black holes to the mysterious push of dark energy, these are the architects of reality, weaving the grand tapestry of existence itself. And today, we're about to uncover 30 of the most powerful among them. But here's the thing: these forces don't just shape distant galaxies. They're the same unseen hands that sculpted the atoms in your body, the light in your eyes, even the thoughts in your mind. You are quite literally made of stardust forged by these titanic powers. Think about that for a moment. Every time you feel the warmth of sunlight or watch the tide roll in, you're witnessing the echoes of forces that could rip planets apart. Gravity, electromagnetism, even the nuclear fires burning inside stars, they're not just abstract ideas in a textbook. They're the heartbeat of the universe, pulsing through everything, everywhere, all at once. And yet, for all their might, most of these forces remain hidden, whispering their secrets only to those who know how to listen. That's where this journey begins. We're about to pull back the curtain on the cosmos, revealing the 30 most astonishing forces that dictate how reality unfolds. Some will be familiar, like the pull that keeps your feet on the ground. Others, well, let's just say they'll challenge everything you thought you knew about how the universe works. This isn't just a list, it's an expedition into the unknown. Along the way, you'll discover forces so strange they defy intuition, like the quantum entanglement that links particles across billions of light years, or the cosmic inflation that stretched the infant universe faster than the speed of light. You'll meet the dark energy accelerating galaxies apart, and the unimaginable pressures inside neutron stars where a teaspoon of matter weighs more than a mountain. And here's the most thrilling part: scientists are still uncovering new forces, rewriting the rules of physics with every discovery. So whether you're a seasoned space enthusiast or just curious about the mysteries overhead, this is your invitation to witness the universe's hidden machinery, the colossal, the bizarre, and the downright mind-bending forces that hold it all together. Ready? Let's begin. Gravity is the silent sculptor of the cosmos, the unseen hand that carved galaxies from chaos and spun planets into orbit. Picture this: without gravity, stars would never ignite, planets would never form, and the universe would be nothing more than a featureless sea of drifting dust. Yet despite its quiet presence, gravity wields unimaginable power. It bends the fabric of space-time itself, warping reality so profoundly that even light cannot escape its strongest grasp. Take something as simple as a falling apple. That gentle tug toward Earth is the exact same force that holds entire galaxies together, keeping billions of stars locked in an endless cosmic dance. But gravity's true might reveals itself in extremes. Inside a black hole, its pull becomes so intense that not even the laws of physics as we know them can resist. Matter gets crushed into a single point of infinite density, a singularity where space and time cease to behave normally. And yet, black holes aren't just destroyers. They're creators too, their immense gravity shaping the galaxies around them, spinning gas and stars into swirling disks that birth new solar systems. Even here on Earth, gravity orchestrates the tides, guiding the moon's embrace of our oceans with a precision that feels almost poetic. What's truly astonishing is how something so universal remains deeply mysterious. We still don't fully understand why gravity is astronomically weaker than other fundamental forces, or how it behaves on the smallest scales where quantum physics takes over. Einstein's theory of relativity gave us a map of gravity's effects, but the journey to uncover its deepest secrets is far from over. Every ripple in space-time, every gravitational wave detected from colliding black holes, brings us closer to decoding the universe's grand design. So the next time you drop a pencil or watch the moon rise, remember, you're witnessing the same force that binds the cosmos together, one invisible thread at a time. If gravity is the universe's sculptor, then electromagnetism is its artist, painting the cosmos with light, energy, and the very bonds that hold matter together. This invisible force governs everything from the glow of distant stars to the spark of a neuron firing in your brain. Picture the atoms in your hand right now, their electrons whirling around nuclei held in place by electromagnetic attraction. That same force, trillions of times stronger than gravity, also fuels the fury of stars, turning hydrogen into helium in a blaze of light that sustains life across the cosmos. Consider something as ordinary as a refrigerator magnet. That simple pull is just a whisper of electromagnetism's true power. At stellar scales, it forges the dazzling auroras that dance across polar skies, charged particles from the sun, snared by Earth's magnetic field in a spectacle of shimmering color. Or think of lightning. A single bolt channels enough energy to power a city, all born from the violent clash of electrical charges in storm clouds. Yet this force isn't just about destruction. Without electromagnetism, molecules couldn't form, water wouldn't exist, and the delicate chemistry of life itself would unravel. The duality of electromagnetism is what makes it so extraordinary. It's the reason your smartphone screen lights up, and the same reason a supernova can outshine an entire galaxy. Deep inside stars, electromagnetic forces push protons so close together that they fuse, unleashing the nuclear fires that illuminate the universe. But here's the twist: electromagnetism also keeps those same stars from collapsing. The repulsion between electrons creates an outward pressure, balancing gravity's crushing grip in a cosmic tug-of-war that defines a star's life. And then there's light itself, electromagnetism's most famous messenger. Every color you've ever seen, from the crimson of a sunset to the eerie glow of a nebula, is just a ripple in this force's endless spectrum. Even when you're gazing at the stars, you're literally seeing electromagnetic handshakes across space, photons that left their source centuries ago, finally meeting your eyes. Yet for all we understand, mysteries remain. Why does electromagnetism dominate at small scales while gravity rules the large? How do quantum fluctuations of this force shape the fabric of reality? Each breakthrough, from harnessing electricity to detecting gravitational waves, reveals just how much more there is to learn. So the next time you flip a light switch or marvel at the northern lights, remember, you're interacting with the same force that stitches atoms together and sets the universe ablaze. Deep inside every atom, an invisible battle rages, a clash so intense it makes the fury of stars seem tame. This is the domain of the strong nuclear force, the universe's ultimate glue, binding atomic nuclei together against unimaginable odds. Without it, matter as we know it would simply dissolve. Protons packed side by side in the nucleus should repel each other violently, their identical positive charges screaming to push apart. But the strong nuclear force overrules this electromagnetic rebellion, gripping particles with a strength 100 times greater than electromagnetism and a staggering 10 to the 38 times mightier than gravity. To grasp its power, picture this. A single teaspoon of neutron star material compressed by this force would weigh 600 million tons on Earth. That's like squeezing Mount Everest into a sugar cube, and it's all thanks to the strong nuclear force's relentless grip. Unlike gravity's endless reach or electromagnetism's flair for spectacle, this force operates on an infinitesimal stage. It works only within the width of a proton, yet its influence echoes across the cosmos. Stars shine because of it, elements form because of it. Even the iron in your blood exists because this force won a billion-year tug-of-war inside ancient stellar furnaces. Here's where it gets stranger. The strong force doesn't just bind protons and neutrons, it's carried by particles called gluons, which act like springs stretched to their limit. The harder quarks, the building blocks of protons, try to pull apart. The tighter the gluons yank them back. It's as if the universe stapled reality together with unbreakable elastic. And when those bonds do snap, like in nuclear fission, the unleashed energy can power cities or devastate them, proving just how much raw power this force locks away. Yet for all its might, the strong nuclear force has a paradoxical fragility. Step barely a proton's width away, and its influence vanishes completely. That's why uranium atoms can decay. Past a certain size, even this mighty force can't hold the nucleus together against electromagnetic repulsion. It's a cosmic balancing act, one that dictates why some elements are stable while others explode or fade. This force's fingerprints are everywhere. In the sun's core, it forges helium from hydrogen, releasing light that warms our world. In supernova, it crafts heavier elements like gold and uranium, scattering them across space. And in particle colliders, scientists recreate its primeval grip, glimpsing conditions last seen microseconds after the Big Bang. The strong nuclear force doesn't just hold atoms together, it holds the story of the universe itself. While the strong nuclear force holds atoms together with an iron grip, its mysterious counterpart, the weak nuclear force, specializes in transformation. This shadowy operator works behind the scenes, rewriting the very identity of particles in ways that shape the fate of stars and planets alike. Imagine a single neutron sitting quietly inside an atom's nucleus. Without warning, the weak force steps in, turning that neutron into a proton, a metamorphosis so profound it sends an electron and a ghostly neutrino flying outward at nearly the speed of light. This is radioactive decay in action, and it's rewriting the elements around you right now. Here's why this matters. Without the weak force, the sun would never shine. Deep in its core, protons fuse to form helium. But the process requires protons to become neutrons, a trick only possible through the weak force's mediation. It's the universe's ultimate alchemist, enabling the nuclear reactions that power stars and forge the building blocks of planets. Even Earth's molten core owes its heat to this force. The radioactive decay of elements like uranium and thorium generates warmth that keeps our planet geologically alive, driving volcanoes and tectonic plates. The weak force operates like a cosmic locksmith, manipulating particles so small they barely exist. Whereas gravity and electromagnetism work across vast distances, this force exerts its influence only within a space 1,000 times smaller than a proton. Yet its effects ripple across the cosmos. Every carbon atom in your body exists because the weak force allowed ancient stars to burn past helium, crafting heavier elements essential for life. And when massive stars die, the weak force helps trigger their explosive demise as supernova, scattering those elements across space like seeds. What makes this force truly bizarre is its preference for left-handed particles, a quirk that breaks the symmetry physicists once thought universal. It's as if the universe has a secret bias written into the fabric of reality itself. Scientists harness this asymmetry in neutrino detectors, capturing flashes of light as these elusive particles, products of weak interactions, zip through Earth by the trillions every second. From keeping stars burning to warming the ground beneath your feet, the weak nuclear force proves that sometimes the smallest players wield the greatest influence. It's a reminder that even in the subatomic shadows, forces are at work reshaping matter, powering worlds, and quietly scripting the story of the cosmos. Dark energy is the universe's greatest unsolved mystery, a shadowy force so powerful it's tearing reality apart. Picture this: every galaxy beyond our own isn't just drifting away, it's accelerating, as if some unseen hand is stretching space itself faster and faster. The Hubble telescope's deep-field images reveal this exodus in haunting detail, ancient galaxies flickering like embers in the void. their light stretched redder over billions of years as the fabric between us and them expands. Gravity, the force that binds planets and stars, should be slowing this cosmic expansion. Instead, something far stranger is winning the tug of war. That something. We call it dark energy, and it makes up nearly 70% of everything in existence. What's baffling is how little we know. Dark energy isn't a substance or a particle, it's more like a property of space itself, an anti-gravity pushing the universe apart. Einstein initially predicted something similar, his cosmological constant, but later dismissed it as a blunder. Now we know space isn't just empty. It hums with latent energy, and as the universe grows, so does its repulsive force. Imagine blowing up a balloon with dots on its surface. The dots move apart naturally as the balloon inflates, but with dark energy, it's as if the balloon starts blowing itself up faster, its rubber stretching at speeds that defy logic. The numbers are staggering. Over the last 5 billion years, dark energy's influence has tripled. Galaxies once close enough to collide now flee beyond our cosmic horizon, their light destined to fade from view forever. If this acceleration continues, distant generations might peer into the sky to find only darkness, our local group of galaxies isolated in an endless black. Yet for all its destructive potential, dark energy also shaped our existence. Without its subtle push in the universe's earliest moments, gravity would have crushed matter back together before stars or planets could form. Here's the cruel irony: the better we measure dark energy, the more confusing it becomes. Some theories suggest it's not constant but evolving, gaining strength or perhaps even fading. Others propose extra dimensions leaking gravity away, making dark energy an illusion. The truth: we're chasing shadows. Every supernova we observe, every map of galaxy clusters, whispers hints that we're missing something fundamental. This isn't just a missing piece of the puzzle, it's a gaping hole where 70% of reality's equation should be. So while gravity builds and the nuclear forces bind, dark energy is the rebel, the force that ensures the cosmos will never settle. It's rewriting the universe's fate, one vanishing galaxy at a time, and we're only beginning to decipher its rules. The deeper we look, the clearer it becomes. Dark energy isn't just a force. It's the question that could redefine physics itself. Dark matter is the universe's silent puppeteer, an invisible hand guiding the fate of galaxies without so much as a whisper of light. Picture a cosmic merry-go-round. Stars at the edge of a galaxy should orbit slower than those near the center, just as outer planets in our solar system move more sluggishly around the sun. But when astronomers measured these rotations, they found something shocking. The outer stars were racing just as fast as the inner ones, as if some unseen mass were anchoring them in place. The only explanation: a colossal halo of dark matter, its gravitational pull keeping galaxies from flying apart. This phantom substance outweighs visible matter 5-to-1, weaving an unseen scaffold that shapes the cosmos. Computer simulations reveal its influence with eerie clarity. Without dark matter's gravitational glue, galaxies would never have formed in the early universe's primordial soup. Particles of ordinary matter, buffeted by radiation, needed dark matter's steady pull to clump together into the first stars and galaxies. Even today, dark matter's fingerprints are everywhere. When light from distant galaxies bends around invisible mass in a phenomenon called gravitational lensing, we're glimpsing its hidden architecture. The Bullet Cluster offers stunning proof. Two colliding galaxy clusters left their gas clouds behind like cosmic smoke, while their dark matter, detected only by its gravity, marched onward unfazed. Yet for all its influence, dark matter remains maddeningly elusive. It doesn't absorb, emit, or reflect light, hence the name. It could be a sea of undiscovered particles, trillions passing through you every second without a trace. Or perhaps it's primordial black holes, forged in the universe's first chaotic moments. Some theories even suggest gravity itself behaves differently at galactic scales, rendering dark matter an illusion. The truth, we've ruled out 90% of initial possibilities, and the remaining candidates, like weakly interacting massive particles or actions, defy detection despite decades of hunting. The stakes couldn't be higher. Dark matter isn't just missing mass, it's the hidden choreographer of cosmic evolution. Its distribution determines where galaxies cluster, how they collide, and even the fate of the universe itself. Future telescopes like NASA's Roman Space Telescope aim to map its web in unprecedented detail, while deep underground detectors listen for the faintest whispers of particle interactions. One thing's certain, solving the dark matter mystery won't just fill a gap in our textbooks, it could rewrite the laws of physics. Until then, every spinning galaxy remains a silent testament to the force we can't see but know must be there. At the heart of nearly every galaxy, including our own Milky Way, lurks a monster so dense it bends the laws of physics, a supermassive black hole. These cosmic behemoths weigh millions to billions of times more than our Sun, packing all that mass into a space smaller than our solar system. Their gravity isn't just strong, it's reality-altering. Picture space-time as a stretched rubber sheet. Now drop a bowling ball onto it. That dent is what a black hole does to the fabric of the universe, warping light, twisting orbits, and slowing time itself to a crawl near its edge. Stars unfortunate enough to wander too close get stretched into spaghetti like streams of plasma, a process called spaghettification before vanishing beyond the event horizon, the point of no return. But here's the paradox: while black holes consume everything, they also create some of the universe's most dazzling phenomena. When gas, dust, and entire stars spiral toward a supermassive black hole, they don't go quietly. Friction heats this infalling material to millions of degrees, forming a swirling disk of superheated plasma that glows brighter than all the stars in its galaxy combined. This is the engine behind a quasar, a cosmic lighthouse so luminous it can be seen across 13 billion light-years of space. Imagine a single object outshining a trillion suns, blazing with the energy of 1,000 supernovae. That's the raw power of a quasar, fueled by a black hole's insatiable appetite. These titans don't just destroy, they shape entire galaxies. The energy unleashed by quasars can blow gas and dust clear across galactic distances, halting star formation and sculpting galactic structure. Some scientists believe quasars even switch off galaxies by ejecting the raw materials needed to make new stars, effectively putting them into retirement. And when two galaxies collide, their central black holes spiral toward each other, eventually merging in a cataclysmic event that shakes spacetime itself, sending gravitational waves rippling across the cosmos. Yet for all their fury, black holes and quasars hold clues to the universe's origins. The light from distant quasars acts like a time machine, revealing what the cosmos looked like when it was just a fraction of its current age. And the supermassive black holes we see today couldn't have grown so large so quickly without some head start, hinting at mysteries still hidden in the early universe. Whether as destroyers, creators, or cosmic probes, these gravitational giants remind us that even in the darkest corners of space, the universe is anything but quiet. Neutron stars are cosmic relics so extreme they defy common sense, stellar corpses where matter gets squeezed beyond recognition. Picture a dying star collapsing under its own weight, crushing all its mass into a sphere no wider than Manhattan. The result, a teaspoon of neutron star material would weigh 1 billion tons on Earth, denser than an atomic nucleus. Atoms themselves cease to exist here. Protons and electrons merge into a swirling ocean of neutrons, packed so tightly they behave like a single, bizarre quantum fluid. Some neutron stars spin hundreds of times per second, their surfaces crackling with mountains barely a millimeter tall. Yet those tiny imperfections warp spacetime enough to emit gravitational waves. But neutron stars have an even more ferocious cousin, magnetars. These rare stellar remnants wield magnetic fields so strong they could strip the data from every credit card on Earth from halfway across the moon. We're talking magnetic forces 1,000 trillion times more powerful than our planet's fields, so intense they twist the very fabric of atoms, stretching electrons into pencil-thin shapes. When a magnetar's crust snaps under this unimaginable strain, it triggers starquakes that ripple through space as gamma-ray flares. In 2004, a magnetar 50,000 light-years away unleashed a burst so energetic it briefly ionized Earth's upper atmosphere despite being far beyond our galaxy's edge. Here's where it gets stranger. Magnetars don't just bend reality, they rewrite physics. Their magnetic fields are strong enough to create particles from pure energy, birthing electron-positron pairs in empty space. Some theories suggest these fields might even alter the properties of light passing through them, slowing photons down like cosmic molasses. Yet for all their violence, magnetars might hold clues to one of astronomy's greatest mysteries, fast radio bursts. These milliseconds-long cosmic signals, some carrying more energy than the sun emits in months, could be magnetar tantrums, magnetic snapbacks sending shockwaves through the universe. Both neutron stars and magnetars serve as laboratories for the impossible, testing the limits of matter, gravity, and quantum forces under conditions we can't replicate on Earth. When two neutron stars collide, an event detected by gravitational waves in 2017, they spray space with gold, platinum, and other heavy elements. That means the ring on your finger might owe its existence to a cataclysmic merger billions of years ago. These stellar remnants remind us that even in death, stars shape the cosmos, forging elements, bending space-time, and occasionally reminding us just how wild the universe can get. Cosmic inflation is the universe's most astonishing magic trick, a fraction of a second when space itself expanded faster than light, transforming a speck smaller than an atom into something the size of a galaxy. Picture the Big Bang not as an explosion in space, but as an explosion of space, a sudden, unfathomable stretching that smoothed and flattened the cosmos like dough in an oven. In less than a trillionth of a second, the universe ballooned by a factor of 10 to the 26, that's a 1 followed by 26 zeros. To put that in perspective, if an atom grew at the same rate, it would become larger than the observable universe in the time it takes light to cross a single proton. This hyper-stretching solves cosmic riddles that baffled scientists for decades. Why does the universe look so uniform in every direction? Because inflation stretched a tiny, homogeneous patch so vast that even today we're only seeing a fraction of it. Why is space so flat with no noticeable curvature? Inflation ironed out any wrinkles, smoothing spacetime like a steamroller over crumpled paper. But the most stunning evidence came in 1992, when satellites detected faint temperature variations in the cosmic microwave background, the afterglow of the Big Bang. Those microscopic fluctuations, like shadows on a cave wall, match predictions of quantum ripples stretched to cosmic scales during inflation. Here's where it gets wild. Inflation implies our universe is just one bubble in an endless froth of expanding realities. Some theories suggest other bubbles may exist beyond our cosmic horizon, each with different physical laws, a multiverse where gravity might be stronger, light slower, or even time itself fractured. And while inflation stopped here 13.8 billion years ago, it may still be happening elsewhere, birthing new universes in an endless cycle of creation. Yet for all its explanatory power, inflation remains controversial. What triggered it? What stopped it? Some physicists argue it's untestable, while others search for primordial gravitational waves, ripples in spacetime from inflation's violent jolt. Whether confirmed or overturned, one thing's certain: inflation reshaped our understanding of reality's origins, revealing a cosmos far stranger and far grander than we ever imagined. Gamma-ray bursts are the universe's ultimate death beams. Cosmic lightning strikes so fierce they can outshine entire galaxies in seconds. Born from the cataclysmic collapse of massive stars or the violent mergers of neutron stars, these bursts channel more energy in 10 seconds than our Sun will emit across its entire 10 billion-year lifetime. Imagine a star 20 times heavier than the Sun detonating in a hypernova, its core collapsing into a black hole while twin jets of plasma, traveling at 99.99% the speed of light, punch through the star's outer layers. These jets, focused tighter than a laser beam, become gamma-ray bursts, the most luminous event since the Big Bang. One such burst, named GRB 030329, rewrote our understanding of cosmic threats in 2004. Originating 50,000 light-years away in the constellation Sagittarius, it unleashed a 500-millisecond pulse of gamma rays powerful enough to ionize Earth's upper atmosphere despite being halfway across the Milky Way. Satellites designed to monitor nuclear explosions blinked in overload, while radio blackouts rippled across the planet. Had this burst occurred within 10,000 light-years, its radiation could have stripped our ozone layer, triggering mass extinctions. What makes gamma-ray bursts so terrifying isn't just their power, it's their unpredictability. They flash without warning, appearing anywhere in the sky at any time. Some last mere milliseconds, others glow for minutes, leaving afterimages in orbiting telescopes. The longest bursts, called collapsars, signal the birth of black holes, while short bursts often betray neutron stars spiraling into oblivion. Their afterglows, lingering X-rays and radio waves, allow astronomers to trace them back to distant galaxies, revealing a universe far more violent than we once imagined. Yet these explosions aren't just destroyers. Gamma-ray bursts might have played a role in shaping life itself. Some theories suggest early bursts sterilized swaths of the cosmos, potentially explaining the Fermi paradox, why we haven't found other civilizations. Others propose that bursts near molecular clouds could trigger star formation, seeding new stellar nurseries with their shockwaves. Even Earth's history might bear their scars. A gamma-ray burst could explain the Ordovician mass extinction 450 million years ago, when 60% of marine species vanished abruptly. Today, networks of satellites and ground-based telescopes scan the skies for these cosmic fireworks, alerting astronomers within seconds of detection. Each burst is a time capsule carrying clues about the early universe's chemistry, the birth of black holes, and the extreme physics of relativistic jets. They remind us that the cosmos isn't just vast and beautiful, it's volatile, unpredictable, and occasionally as deadly as it is dazzling. The Sun isn't just a gentle ball of light, it's a seething, hyperactive powerhouse capable of hurling billion-ton tantrums into space. Solar flares and coronal mass ejections are its most dramatic outbursts, eruptions of energy so vast they can reshape the space around our planet in an instant. A solar flare is like a cosmic lightning strike, a sudden, intense burst of radiation across the electromagnetic spectrum, from radio waves to gamma rays. In just minutes, a single flare can release the energy of 10 million volcanic eruptions, heating solar plasma to tens of millions of degrees. But flares are just the opening act. The real spectacle comes when the Sun's outer atmosphere, the corona, unleashes a coronal mass ejection, or CME. These are billion-mile-wide tsunamis of magnetized plasma, racing outward at speeds up to 2 million miles per hour. If Earth lies in their path, the results can be catastrophic. Take the Carrington event of 1859, the most powerful solar storm ever recorded. Telegraph operators watched in awe as sparks leaped from their equipment, some even sending messages with the batteries disconnected, powered solely by auroral currents. Nighttime skies turned blood red as far south as Cuba, with auroras so bright they cast shadows. Birds, confused by the unnatural daylight, began singing at midnight. Today, a storm of that magnitude would wreak havoc on our technology-dependent world. satellites could be fried by intense radiation, GPS signals scrambled, and power grids overwhelmed by geomagnetic currents. Transformers, the backbone of electrical infrastructure, might melt under the strain, triggering blackouts lasting months. What makes these solar outbursts so dangerous is their unpredictability. Unlike hurricanes or earthquakes, we get little warning, sometimes just hours before a CME slams into Earth's magnetic field. The sheer scale is hard to grasp. A single CME can dwarf our entire planet, carrying enough energy to power global civilization for years. When these charged particles collide with Earth's magnetosphere, they don't just create pretty auroras. They induce electrical currents in pipelines, railroad tracks, and undersea cables, anything long and conductive. In 1989, a far weaker solar storm than the Carrington event blacked out Quebec's power grid in seconds, leaving millions in the dark. Yet these solar tantrums also reveal the sun's hidden dynamics. Flares and CMEs erupt from tangled magnetic fields, snapping like overstretched rubber bands, releasing pent-up energy in seconds. The sun's surface dances with vast loops of plasma, each one a potential storm waiting to happen. And while we've gotten better at spotting warning signs, sunspot clusters, magnetic complexity, we're still at the mercy of our star's whims. Future missions like NASA's Parker Solar Probe aim to predict these eruptions by studying the sun's corona up close, braving temperatures hot enough to vaporize steel. So the next time you see an aurora's shimmering curtain, remember, that beautiful light show is a glimpse of the sun's raw power, a force capable of both inspiring wonder and plunging civilization into chaos. It's a humbling reminder that even our most advanced technology is no match for the universe's untamed fury. Galactic collisions are the ultimate cosmic slow-motion wreck, a dance of destruction and creation spanning billions of years. Right now, our Milky Way is on an unavoidable collision course with Andromeda, our closest galactic neighbor. Picture two titanic spirals, each containing hundreds of billions of stars, drifting toward each other at 250,000 miles per hour. Yet despite that staggering speed, the sheer distances mean this crash won't fully unfold for another 4 billion years. When it does, the night sky will transform into something unrecognizable, a swirling canvas of newborn stars, warped spiral arms and tidal tails stretching across the heavens like celestial brushstrokes. What's astonishing is how little violence this collision will actually involve. While galaxies appear solid, they're mostly empty space. Stars are so far apart that direct collisions will be vanishingly rare. Instead, gravity's invisible hand will reshape both galaxies through tidal forces, the same kind of pull that Earth exerts on our oceans to create tides, but amplified to cosmic proportions. Andromeda's gravity will stretch the Milky Way's disk, flinging stars into elongated streams while its own spiral arms unravel like a spinning top losing balance. Over eons, the two galaxies will merge into a single elliptical blob. Scientists whimsically call it Milkdromeda, a golden-hued city of aging stars with no trace of its former spiral elegance. But not all galactic encounters end so peacefully. When smaller galaxies plunge into larger ones, tidal forces can rip them apart entirely. The Large Magellanic Cloud, a satellite galaxy orbiting the Milky Way, is currently being shredded by our galaxy's gravity, leaving a glittering trail of stars known as the Magellanic Stream. And in the depths of space, galaxies like the Tadpole Galaxy sport tales hundreds of thousands of light-years-long ghostly evidence of past collisions where gravity sculpted stellar debris into cosmic artwork. Tidal forces reach their most extreme near black holes, where gravity's pull becomes so unbalanced it can stretch objects into noodles. This gruesome process spaghettification occurs when the difference in gravity between your head and feet becomes stronger than the molecular bonds holding you together. A hapless star wandering too close to a supermassive black hole doesn't just get torn apart. It's stretched into a thin strand of plasma, glowing brilliantly as friction heats it to millions of degrees. Astronomers have witnessed these tidal disruption events, watching as black holes feast on stellar spaghetti, their accretion disks flaring brighter than quasars for months. Yet for all their destructive power, galactic collisions and tidal forces are also creators. The violent compression of gas during mergers triggers furious waves of star formation, lighting up newborn stellar nurseries. Many of the universe's most massive stars, and by extension, the black holes and neutron stars they leave behind, owe their existence to these chaotic encounters. Even our own solar system might be a product of ancient tidal forces, born during a long-ago brush with a passing galaxy. So while the Milky Way's fate is sealed, its collision with Andromeda won't be an end, just the next fiery act in an ever-evolving cosmic story. Vacuum decay isn't just a theory, it's the universe's ultimate reset button, a silent catastrophe waiting in the quantum shadows. Picture this: a single point in space, smaller than an atom, suddenly becomes the epicenter of a new reality where physics as we know it ceases to exist. This domino effect begins with the Higgs field, the invisible energy field that gives particles their mass which might not be in its most stable state. Like a pencil balanced on its tip, our universe could be teetering on a precarious quantum ledge, and one tiny nudge could send it tumbling into an entirely new set of physical laws. Scientists call this a false vacuum state. If even one quantum fluctuation causes the Higgs field to drop to a lower energy level, it would create an expanding bubble of true vacuum. This bubble would race outward at the speed of light, rewriting fundamental constants in its wake. The speed of light might change, atoms could lose their ability to bind. Even time itself might flow differently beyond that boundary. What makes this so chilling is the absence of warning. By the time you saw the bubble coming, it would already be upon you, erasing existence as effortlessly as a wave washing away footprints in sand. Eerie simulations reveal how this would unfold. A blue sphere appears in the void, the new universe's frontier growing exponentially as it converts everything it touches. Planets, stars, and galaxies wouldn't explode or collapse. They'd simply stop working, their matter no longer obeying the rules that once held them together. Civilizations, if any survived long enough to witness it, wouldn't even have time to process their doom. The laws of physics themselves would unravel mid-thought. Yet for all its horror, vacuum decay might already have happened elsewhere. The cosmos is so vast that bubbles of true vacuum could be expanding right now, billions of light years away, their death fronts racing toward us at light speed. Some theories even suggest this could explain dark energy, that we're seeing the aftermath of distant vacuum decays warping spacetime. Others propose that our universe itself is the result of an earlier decay, a cosmic phoenix born from the ashes of a previous physics. The stakes couldn't be higher. If vacuum decay is possible, then every particle collision in every lab, every cosmic ray strike, every random quantum fluctuation carries existential risk. It's like living in a house made of matchsticks where one stray spark could rewrite the blueprint of reality. And yet here's the twist: this very instability might be why our universe permits life at all. The fragile balance of the Higgs field allows for the complexity that builds stars, planets, and minds capable of contemplating their own annihilation. So while the odds remain vanishingly slim, vacuum decay forces us to confront a profound truth. The universe isn't just unpredictable, it's provisional, a temporary arrangement of forces that could, at any quantum moment, decide to play by new rules. Whether as a distant specter or a lurking threat, it reminds us that physics isn't fixed, it's a story still being written, one precarious equation at a time. Quantum entanglement defies everything we think we know about reality, a phenomenon so bizarre Einstein himself called it spooky action at a distance. Picture two particles born from the same quantum event, like twins sharing an invisible bond. Separate them by billions of light years, and here's the twist: measuring one instantly determines the state of the other, as if they're whispering secrets across the void faster than light could ever travel. This isn't just theoretical. In labs worldwide, scientists have entangled particles and observed this eerie synchronization with photons, electrons, and even tiny diamonds, all playing by these counterintuitive rules. The implications shatter classical physics. Under Newton's laws, information can't travel faster than light. It's the universe's ultimate speed limit. Yet entanglement suggests a deeper layer of reality where particles communicate instantaneously, as if space and time are illusions. Imagine flipping a coin in New York and another in Tokyo, and every time yours lands heads, the other always lands tails, no matter how quickly you check. That's entanglement in action, a correlation so perfect it hints at a hidden quantum fabric stitching the cosmos together. Here's where it gets even stranger. Entanglement isn't just some microscopic curiosity. Some theories propose it might scale up with macroscopic objects or even living beings sharing entangled states. Experiments have entangled thousands of atoms simultaneously, and researchers suspect photosynthesis in plants might exploit quantum effects for efficiency. Could entanglement weave through the fabric of life itself? The possibility tantalizes scientists probing the boundary between quantum mechanics and biology. But the real revolution lies in its potential for quantum communication. While entanglement can't transmit messages faster than light, a common misconception, it enables unhackable quantum encryption. China's Misha satellite, for instance, sent entangled photon pairs to ground stations 1,200 kilometers apart, creating a secure key no eavesdropper could crack without detection. Future quantum networks might span continents, linking computers with security guaranteed by the laws of physics, yet mysteries remain. Does entanglement require hidden variables we haven't discovered, or is the universe fundamentally non-local, with particles influencing each other beyond space-time's reach? Every experiment peels back another layer, revealing a cosmos far stranger than fiction, one where particles dance to a tune we're only beginning to hear. Neutrinos are the universe's ultimate ghost, shadowy particles so elusive they pass through planets like they're not even there. Trillions stream through your body every second, remnants of nuclear reactions in the sun, distant supernova, and even the Big Bang itself. These cosmic phantoms carry no charge, nearly no mass, and interact so weakly with matter that detecting them is like trying to catch smoke with a butterfly net. Yet their very elusiveness makes them priceless messengers, offering clues about the cosmos that light alone could never reveal. Buried deep beneath the Antarctic ice lies one of the most daring neutrino hunts in history, the Ice Cube Observatory. Picture a cubic kilometer of pristine ice, studded with over 5,000 light-sensitive detectors. When a rare neutrino does collide with an atom in the ice, it creates a faint blue flash called Cherenkov radiation, a shimmering trail that Ice Cube's sensors trace back to its origin. In 2013, this frozen labyrinth captured neutrinos from beyond our galaxy, marking the first time we'd traced cosmic rays to their distant sources. Some of these particles had traveled for billions of years, their paths undisturbed by magnetic fields or dust, pointing like arrows back to supermassive black holes and colliding galaxies. What makes neutrinos revolutionary isn't just where they come from, it's what they tell us about how the universe works. During supernova 1987A, neutrinos arrived on Earth hours before the dying star's light, proving they escape a collapsing star's core faster than photons can fight through the chaos. Today, neutrino detectors act like cosmic early warning systems, poised to alert astronomers the moment a star explodes in our galactic neighborhood. Even more bizarre, neutrinos oscillate, changing flavors between electron, muon, and tau types mid-flight. A discovery that upended particle physics and confirmed they have mass, however infinitesimal. The hunt for these ghostly particles keeps pushing technology to its limits. Beneath the Mediterranean, the KM3 detector stares into the abyss with thousands of optical modules, while Japan's Super Kamiok and watches a tank of ultra-pure water for the faintest gleam of neutrino interactions. Future experiments aim to catch relic neutrinos from the Big Bang itself, a fossil glow that could reveal the universe's earliest moments, from unlocking the sun's inner workings to exposing flaws in the standard model. These silent wanderers remind us that sometimes the most powerful forces are the ones we can barely sense at all. Cosmic rays are the universe's invisible bullets, high-energy protons and atomic nuclei screaming through space at nearly the speed of light. Born in the violent aftermath of supernova or ejected by distant quasars, these particles carry enough energy to punch through solid lead, yet they're so tiny that trillions pass harmlessly through your body every second. But every now and then, one strikes with consequences that ripple across millennia. When a cosmic ray collides with Earth's atmosphere, it shatters air molecules into a shower of secondary particles, some of which reach the ground, and a few of those, by sheer chance, will collide with the atoms in your DNA. These microscopic interactions have shaped life in ways we're only beginning to understand. Over eons, cosmic rays have acted as nature's random mutagen, subtly altering genetic codes and driving evolution forward. Without them, the genetic diversity that fuels adaptation and ultimately survival might have stalled, but their influence doesn't stop there. When cosmic rays strike nitrogen in the atmosphere, they transform it into carbon-14, the radioactive isotope that allows us to carbon date ancient artifacts and fossils. Every mummy, every fossilized bone, every relic of human history carries traces of these interstellar visitors, their decay ticking like a cosmic clock. Yet cosmic rays also hold clues to the universe's most extreme environments. The highest energy particles detected, dubbed "oh my god" particles, pack the kinetic energy of a fast-pitched baseball but compressed into a single proton. Where do such monstrous energies come? Some might originate in the relativistic jets of supermassive black holes, where magnetic fields act as cosmic particle accelerators, flinging matter across galaxies. Others could be debris from neutron star collisions or as yet unknown cosmic catastrophes. On Earth, scientists chase these particles with detectors buried underground, suspended from balloons, or even strapped to high-altitude planes. The Pierre Auger Observatory in Argentina spans an area the size of Rhode Island, its 1,600 water tanks waiting for the faint blue glow of a cosmic ray strike. Meanwhile, space telescopes like the Fermi Gamma Ray Space Telescope trace the aftermath of these collisions, mapping the high-energy universe in unprecedented detail. But cosmic rays aren't just relics of the distant cosmos, they're a present-day challenge. Astronauts on the ISS face increased exposure, their bodies bombarded by particles that Earth's magnetic field would normally deflect. Future missions to Mars will need shielding against this invisible rain, or risk DNA damage that could jeopardize the entire journey. Even our technology isn't immune. Cosmic rays have been known to flip bits in computer memory, causing glitches in everything from satellites to smartphones. From mutating ancient life forms to threatening modern space travel, cosmic rays are a reminder that we're not separate from the universe, we're part of its endless conversation. Every time one pierces the atmosphere, it carries a message from the depths of space, written in the language of energy and chance. And as we learn to decode that message, we uncover not just the secrets of distant stars, but the invisible forces that have shaped our own story from the very beginning. If black holes are the universe's one-way doors, then wormholes might just be its secret passageways, hypothetical tunnels through the fabric of spacetime itself. Picture folding a piece of paper so two distant points touch, then piercing through with a pencil. That's the essence of a wormhole, a shortcut between realms that could, in theory, connect opposite sides of the universe or even bridge different timelines. While Einstein's equations allow for their existence, no one's ever spotted one. The catch: wormholes would require exotic matter with negative energy to stay open, something we've never observed. Without it, these cosmic hallways would snap shut faster than a slamming airlock, crushing anything inside. Yet the possibility tantalizes physicists and storytellers alike. Imagine a spacecraft diving into a glowing ring of distorted starlight, emerging moments later in a galaxy a billion light-years away. It's the stuff of Interstellar's breathtaking visuals, but the science behind it is razor-thin, balanced on equations that might never manifest in reality. Now flip the script entirely, because if wormholes are speculative backdoors, white holes are their bizarre, theoretical opposites. While a black hole's gravity is so strong nothing escapes, a white hole violently expels matter and energy, forbidding anything from entering. Think of it as a cosmic fire hydrant, blasting out space-time like an unstoppable geyser. Some theories suggest white holes could be the other end of a black hole's tunnel, spewing out whatever fell in elsewhere. Others propose they're remnants of the Big Bang itself, final bursts of a primordial singularity. But here's the twist: no white hole has ever been observed. They might be mathematical phantoms, or they could simply be too short-lived to catch, a universe-scale firework flashing into oblivion in seconds. The irony is delicious. Black holes, once dismissed as mathematical oddities, are now known to lurk in every galaxy's heart. Wormholes and white holes, meanwhile, remain tantalizing ghosts in the equations. Yet their allure persists because they challenge our intuition about space, time, and the limits of physics. Could a civilization harness wormholes to traverse the stars? Might white holes explain mysterious gamma-ray flashes in the cosmos? For now, these questions linger at the edge of theory, where science bleeds into dreams of what might lie beyond the known universe's veil. Plasma isn't just a state of matter. It's the universe's dominant ingredient, a seething ocean of ionized particles that shapes everything from solar flares to the largest structures in the cosmos. Picture the sun's corona, where temperatures soar to millions of degrees, stripping atoms bare and turning gas into an electrified soup of free electrons and nuclei. This isn't some rare extreme. Over 99% of the visible universe exists as plasma, from the shimmering auroras dancing over Earth's poles to the vast interstellar clouds where stars are born. What makes plasma so extraordinary isn't just its ubiquity, it's how it dances to the tune of cosmic magnetic fields, weaving invisible threads of force that stretch across light years. Take the solar wind, a relentless stream of charged particles racing outward from the sun at 1,000,000 miles per hour. As this plasma flood slams into Earth's magnetic field, it doesn't just dissipate, it funnels along magnetic lines, spiraling toward the poles in a dazzling light show. The same phenomenon paints Jupiter's auroras with colors so intense they outshine the planet's reflected sunlight, powered by magnetic fields 20,000 times stronger than Earth's. But the solar wind's influence doesn't stop there. Over eons, it stripped Mars of its atmosphere, scouring away water and air until the planet became the barren desert we see today. Venus, by contrast, fights back with a runaway greenhouse effect, its thick atmosphere resisting erosion. But even there, the solar wind claws away 100 tons of ionized gas every hour. Now zoom out to the galactic scale. Between galaxies lies the cosmic web, a sprawling network of plasma filaments, magnetized and glowing faintly with the heat of countless stars. These aren't static structures, they're dynamic rivers of charged particles, channeled and twisted by magnetic fields that might span millions of light years. When galaxies collide, their magnetic fields tangle like spaghetti, amplifying to strengths that can accelerate particles to near light speed. Some astronomers believe these colossal magnetic webs even guide the growth of galaxies themselves, funneling gas into star-forming regions like invisible cosmic aqueducts. Yet for all their power, cosmic magnetic fields remain eerily elusive. They leave no direct light signature, only traces in the way they bend the paths of charged particles or polarized starlight. To map them, scientists use radio telescopes to detect the faint synchrotron radiation emitted by electrons spiraling around magnetic lines, a glow that reveals the hidden scaffolding of the universe. The most stunning example, the Milky Way's own magnetic field, a sprawling spiral that mirrors our galaxy's shape, its lines twisting like the grooves of a record. What's truly mind-bending is how these forces intertwine. Plasma without magnetic fields would be chaos, a turbulent sea without direction. Magnetic fields without plasma would have nothing to shape. Together, they're the architects of cosmic weather, steering solar storms, sculpting nebulae, and perhaps even seeding the conditions for life itself. The next time you see a lightning bolt or the shimmer of the northern lights, remember, you're witnessing a fragment of the same forces that weave the universe together, one charged particle at a time. The Big Bang wasn't just an explosion, it was the moment reality itself blinked into existence, a singularity of infinite density and temperature suddenly stretching into the cosmos we know today. Picture all the matter in the observable universe compressed into a point smaller than an atom, then abruptly expanding faster than light itself during inflation. That first searing flash still lingers as the cosmic microwave background, a faint afterglow permeating every corner of space, discovered accidentally in 1965 when radio astronomers stumbled upon mysterious static coming uniformly from all directions. That hiss of microwaves just 3 degrees above absolute zero is literally the cooled remnants of the universe's fiery birth, redshifted over 13.8 billion years into a ghostly whisper. But the cosmic microwave background isn't just a relic, it's a snapshot of the infant universe, etched with subtle temperature variations that reveal the seeds of all future structure. Those tiny fluctuations, mere 1 part in 100,000 differences in heat, correspond to regions where matter was ever so slightly denser. Over eons, gravity amplified those wrinkles into the vast web of galaxies and voids we see today. It's like finding the fossilized footprints of a cosmic giant preserved in the microwave haze. Satellites like Planck and WMAP have mapped this primordial tapestry in exquisite detail, their data aligning so perfectly with Big Bang predictions that it's eerie. The universe didn't just begin, it left a fingerprint. What's staggering is how much emerged from that initial singularity. Within the first second, quarks condensed into protons and neutrons, while photons and neutrinos ricocheted through the seething plasma. By 3 minutes, the first atomic nuclei, hydrogen and helium, had formed in the furnace of nucleosynthesis. Yet for 380,000 years, the universe remained opaque, a fog of charged particles scattering light relentlessly. Then, in a pivotal moment called recombination, everything cooled enough for electrons to latch onto nuclei, creating neutral atoms. Suddenly, photons could travel freely, their first voyage beginning the cosmic microwave background we detect today, a baby picture of the cosmos when it was just 0.003% its current age. But the Big Bang's legacy isn't just in the past. Its echoes shape cutting-edge physics, from the hunt for gravitational waves generated in inflation's first tremors to the mystery of why matter outraced antimatter in those early moments. Some theories even suggest our universe is just one bubble in an infinite multiverse, each with its own Big Bang and perhaps its own laws of physics. The deeper we probe, whether through particle colliders recreating quark-gluon plasma or telescopes peering back to the dark ages before stars, the more we realize how much of the story remains unwritten. The Big Bang isn't a closed chapter, it's the first line of an epic still unfolding, written in microwaves, elemental abundances, and the very fabric of space-time. Black holes aren't the cosmic vacuum cleaners we once thought. They're more like sieves, slowly leaking energy back into the universe thanks to a bizarre quantum quirk called Hawking radiation. Picture the edge of a black hole, the event horizon where gravity's grip is so fierce that not even light can escape. But right at this boundary, something extraordinary happens. Quantum mechanics tells us that empty space isn't really empty, it's a seething foam of particle-antiparticle pairs popping into existence and annihilating each other in an endless dance. Normally, these fleeting particles vanish without a trace, but near a black hole, the gravitational tidal forces can wrench them apart, sending one particle plummeting into the abyss while the other escapes into space. This isn't just theoretical poetry. The escaped particles carry energy away from the black hole, causing it to lose mass over time, a process Stephen Hawking first calculated in 1974. His voice, captured in archival recordings, once mused on the irony: "Black holes ain't so black after all. The smaller the black hole, the faster it evaporates." A black hole with the mass of a mountain would glow furiously, radiating away its entire existence in a cosmic blink. But a supermassive one, like the beast at the center of our galaxy, it would take longer than the current age of the universe to shed even a fraction of its bulk. Here's the twist: Hawking radiation isn't just a slow leak, it's a death sentence. As a black hole evaporates, it heats up, radiating faster and faster until, in its final moments, it erupts in a burst of gamma rays. For a brief instant, that dying black hole would shine brighter than 1,000 stars, a final defiant scream against oblivion. Yet no one's ever witnessed this spectacle. The universe is too young for any black hole to have fully evaporated so far. But Hawking radiation isn't just about destruction. It's a bridge between two seemingly incompatible theories: gravity and quantum mechanics. The fact that black holes can radiate suggests they have temperature, entropy, even a sort of quantum memory. These clues hint at a deeper truth about how space-time and matter intertwine at the most fundamental level. Some physicists believe decoding Hawking radiation could unlock the secrets of a theory of everything, revealing how the universe stitches together the very large and the very small. So the next time you gaze at the night sky, remember, even the darkest voids aren't silent. They hum with quantum whispers, slowly unraveling one particle at a time. The Milky Way hides a secret: two colossal gamma-ray bubbles towering 50,000 light-years above and below our galaxy's core. These are the Fermi bubbles, discovered in 2010 by NASA, a Fermi gamma-ray space telescope, and they glow with the faint but unmistakable signature of high-energy radiation. Imagine twin cosmic hourglasses, each large enough to contain a dozen Milky Ways stacked end to end, their edges sharp as razors against the dark backdrop of intergalactic space. What could have carved such enormous structures out of the galaxy's halo? The leading suspect, a ravenous black hole binge-eating session 4 million years ago, when Sagittarius, a star, the supermassive black hole at our galaxy's heart, last awoke from its slumber. The scale of this ancient eruption defies imagination. Picture a belch so powerful it blasted trillions of tons of superheated gas and cosmic rays outward at nearly the speed of light, inflating these bubbles like balloons. The energy involved, roughly 100,000 supernova exploding simultaneously. That's enough raw power to sterilize entire swaths of the galaxy, yet Earth, safely distant in the galactic suburbs, was spared. Today, the bubbles remain as faint, shimmering ghosts, their gamma rays tracing the contours of this prehistoric cataclysm. But their discovery rewrote our understanding of galactic black holes. Once thought dormant titans, they're now known to be intermittent monsters, capable of reshaping their host galaxies in violent outbursts. What's truly baffling is the bubble's crisp, defined edges. Simulations suggest such clean boundaries would require the original eruption to have been incredibly brief, perhaps a single, devastating surge lasting no more than 100,000 years. That's a cosmic eye blink compared to the Milky Way's 10 billion-year history. It's as if Sagittarius, a star, woke up, screamed into the void, then promptly fell back asleep, leaving behind these eerie monuments to its hunger. But the Fermi bubbles aren't just relics. They're active laboratories, their high-energy particles offering clues about the extreme physics near black holes. Some theories propose they're filled with exotic dark matter annihilations, while others suggest they're colossal particle accelerators flinging cosmic rays across the galaxy. One thing's certain, whatever birthed them left an indelible mark on the Milky Way, a reminder that even our seemingly quiet galactic home harbors a violent past and perhaps an equally turbulent future. Deep in the direction of the constellations Centaurus and Hydra, something colossal is pulling at our galaxy and everything around us with irresistible force. This is the Great Attractor, a gravitational anomaly so powerful it's dragging thousands of galaxies toward it at breakneck speeds, including our own Milky Way. Imagine the cosmic web as a vast river system, with galaxies as leaves caught in the current, all flowing toward this single, enigmatic point in space. The strange part, we can't even see what's doing the pulling. The Great Attractor lies hidden behind the thick dust and stars of our galaxy's disk, shrouded in what astronomers call the zone of avoidance, a swath of sky where the Milky Way's own brilliance blinds our telescopes to what lies beyond. For decades, this region was astronomy's blind spot. Visible light telescopes saw only a dazzling wall of nearby stars, but X-ray and radio observations eventually pierced the veil, revealing an astonishing truth: the Great Attractor isn't acting alone. It appears to be part of something even larger, the Laniakea supercluster, a sprawling filament of galaxies spanning 500 million light-years, with the Great Attractor sitting near its core like a spider at the center of a gravitational web. Here, the mass of 100,000 Milky Ways conspires to bend spacetime itself, sculpting the motion of everything in our celestial neighborhood. Our galaxy, along with Andromeda and countless others, is surfing this cosmic tide at nearly 2 million kilometers per hour toward an unseen destiny. Yet the Great Attractor's grip is just a local tug in an even grander cascade. Beyond it lies the Shapley supercluster, an even more massive concentration of galaxies pulling the Great Attractor itself, a cosmic game of gravitational dominoes stretching across the observable universe. This hierarchy of attractors reveals a startling truth: the universe isn't expanding uniformly. Like cream swirling in coffee, matter clusters in vast flows and voids, with galaxies riding currents we've only begun to chart. The irony is delicious. For all our grand cosmic maps, one of the most influential forces in our galactic backyard remained nearly invisible until modern technology caught up. Infrared surveys like those from the Spitzer Space Telescope have now sketched the great ATTRACTORS Chinese letter, detecting galaxies previously lost in the glare. What they've found is both humbling and exhilarating, a reminder that even as we peer billions of light years outward, some of the universe's greatest mysteries are hiding quite literally in our own shadow. At the smallest scales imaginable, far tinier than an atom, even smaller than a proton, spacetime itself churns with violent turbulence like a stormy sea seen through a microscope. This is the realm of quantum foam, where the smooth fabric of reality dissolves into a froth of fleeting particles and voids, blinking in and out of existence so quickly they barely register as more than statistical noise. Imagine zooming in on the surface of a calm pond until you see the water isn't smooth at all. Instead, it's a chaotic dance of bubbles forming and popping at random. Now replace the water with spacetime and those bubbles with pairs of virtual particles, and you've got a glimpse of the universe's most frenetic backstage activity. These particles aren't mere mathematical abstractions. They're real enough to leave fingerprints on the cosmos. In empty space, what we once thought of as pure nothingness, quantum foam ensures that zero-point energy is never truly zero. Particles and their antiparticle twins materialize from the void, borrowing energy from the universe in a fleeting act of defiance against the laws of classical physics. Most vanish before they can be measured, annihilating each other in bursts of energy so brief they're practically ghosts. But sometimes, when conditions are just right, these apparitions leave lasting marks. Near the event horizon of a black hole, for instance, tidal forces can wrench these particle pairs apart, with one falling into oblivion while the other escapes as Hawking radiation, the slow leak that dooms black holes to eventual evaporation. What's even wilder is that this foam isn't just a side effect. It might rewrite our understanding of spacetime's very structure. At the Planck scale, a distance of 10 to the minus 35 meters, quantum fluctuations are so violent that spacetime itself could become granular like pixels on a screen. Traveling through this foam at ultra-small scales would be like trying to swim through a hurricane, with time and space losing all semblance of smooth continuity. Some theories suggest that if we could probe these depths, we'd find microscopic wormholes woven into the foam's fabric tunnels threading through the chaos, connecting distant points in spacetime like shortcuts through a maze. Yet for all its turbulence, quantum foam isn't just chaos. It's the reason atoms don't collapse, why empty space crackles with latent energy, and how the universe manages to balance itself on the knife's edge between stability and dynamism. Without this seething undercurrent, the vacuum of space would be inert, and the cosmos as we know it couldn't exist. Future experiments like advanced gravitational wave detectors or tabletop quantum gravity simulations aim to catch glimpses of this frothy reality, hints of a universe far stranger and far more alive than we ever imagined. So the next time you look up at the serene night sky, remember, beneath the calm, spacetime is boiling. Here's a wild thought. What if the universe doesn't just exist, but knows it exists because we're here to witness it? At the heart of quantum mechanics lies one of science's most mind-bending puzzles, the observer effect. It's the strange phenomenon where simply measuring a particle seems to force it to choose a state, as if reality itself waits for conscious observation to snap into focus. In the famous double-slit experiment, particles behave like waves when no one's looking, creating interference patterns on a screen. But the moment scientists set up detectors to observe which path a particle takes, the wave-like behavior vanishes like a shy actor freezing under a spotlight. This isn't just lab table quirkiness. Some interpretations, like the Copenhagen school of thought, suggest reality remains an unresolved blur of probabilities until an observer, maybe you, maybe a machine, forces it to collapse into concrete existence. The implications are staggering. Does the moon exist when no one's looking? Did galaxies spin in darkness before the first life forms evolved to witness them? Physicists like John Wheeler took this even further with his participatory universe hypothesis, proposing that consciousness isn't just a passive spectator but an active ingredient in creation, retroactively shaping reality back to the Big Bang. Now, before you start thinking you've unlocked God mode, here's the twist. Not all scientists buy into consciousness as a cosmic keystone. Critics argue the observer effect is just about measurement's physical impact, not sentience. A camera or a Geiger counter can collapse quantum states, no human required. And yet here's where it gets eerie. Alternative theories like quantum Darwinism suggest that stable reality emerges precisely because countless interactions select durable states, like an evolutionary process for facts. In other words, the universe needs observers not because of human specialness, but because consistent reality requires shared agreement. So where does that leave us? If consciousness truly does play a role in shaping existence, then humanity isn't just an accident on a lonely rock. We might be the universe's way of understanding itself. But if not, the mere fact that we can ponder this question still ties us into something profound. Whether passive witnesses or cosmic collaborators, our curiosity alone has unraveled black holes, traced the birth of stars, and glimpsed the quantum foam beneath spacetime. And that raises one final, chilling possibility. If observation shapes reality, what happens when we turn our attention to the next great mystery and find it staring back? From the universe-shattering power of gamma-ray burst to the eerie whispers of quantum foam, we've witnessed forces so immense and so bizarre, they make our human-scale struggle seem microscopic. Let's revisit 5 that redefine the word extreme. At number 5, dark energy, the phantom force ripping the cosmos apart at an ever-accelerating pace. Imagine a universe where galaxies aren't just drifting away but fleeing, vanishing beyond an unreachable horizon. It's a slow-motion apocalypse written into the fabric of space itself, and we still don't know why. Number 4, supermassive black holes. These aren't just cosmic vacuum cleaners, they're reality warping titans that sculpt entire galaxies. When they feed, quasars ignite, outshining 1 trillion suns. When they collide, gravitational waves ripple through space-time, carrying echoes of violence older than Earth itself. Then there's third place, where vacuum decay lurks, a quantum doomsday that could rewrite physics in an instant. One tiny fluctuation and a bubble of new reality expands at light speed, erasing atoms, stars, and even time as we know it. The chilling part, it might already be happening somewhere in the void. Second place goes to neutron stars, where a sugar cube of matter weighs more than a mountain. Spin one fast enough, and its magnetic field strong enough to shred atoms from light years away, birth magnetars. These cosmic monsters unleash starquakes so violent they briefly outshine the Milky Way. But topping our list, quantum entanglement, 2 particles separated by billions of light years, mirroring each other instantly, faster than light, defying locality, and making Einstein himself call it spooky. It's proof that beneath reality's calm surface, the universe plays by rules we're only beginning to guess. These forces don't just dwarf human power, they humiliate it. A gamma-ray burst could sterilize a galaxy while we fret over smartphone batteries. Dark energy stretches space itself while we measure our lives in decades. Yet here we are, tiny and tenacious, mapping the chaos with math and curiosity. So tell us which cosmic force left you awestruck. Vote in the comments, and if you're hungry for more universe-shaking mysteries, hit subscribe. Because out there, beyond the edge of our understanding, reality's strangest chapters are still being written, and you've got a front row seat.